Welcome to this lecture on mosquito-borne diseases. Today, we are going to explore one of the most fascinating and critical topics in public health. We will learn exactly how microscopic pathogens use mosquitoes to spread devastating diseases across human populations, and more importantly, how we can use mathematics to predict and stop them. To begin our journey, let us think of a mosquito as a tiny flying syringe. When a mosquito bites someone who is already sick, it drinks up microscopic germs along with its blood meal. Later, when it lands on a healthy person to feed again, it spits a little bit of saliva into the skin to stop the blood from clotting. During that exact moment, those hidden germs slip into the new bloodstream. It is crucial to remember that the mosquito itself does not make you sick. It is merely the biological vector, or transport vehicle, for these microscopic hitchhikers. Now that we understand the mosquito's role as a transport vehicle, let us look at the actual hitchhikers causing the harm. There are different types of pathogens that rely on this method of travel. For instance, malaria is caused by a parasite that undergoes complex life stages inside the mosquito. On the other hand, diseases like dengue and chikungunya are caused by viruses. Regardless of whether the pathogen is a parasite or a virus, they all depend entirely on the mosquito to move from one human host to another, making the mosquito the ultimate enabler of these diseases. Building on the types of pathogens, we must understand that transmission is not instantaneous. This is called biological transmission. Once the mosquito ingests the pathogen, the germ must undergo a necessary period of development, or multiplication. It first incubates in the mosquito's gut. Over several days, it carefully migrates to the salivary glands. Only when it is safely positioned in the salivary glands can it be injected into a new, healthy host during a subsequent blood meal. This fascinating but dangerous biological journey is what completes the transmission cycle. To visualize this biological journey we just discussed, let us look at this diagram of the transmission cycle. On the left, you see the first infected human. The cycle begins with the first bite, where the mosquito ingests the pathogen. Notice the clock icon inside the mosquito. This represents the extrinsic incubation period, the crucial time the pathogen needs to develop. Below the mosquito is a skull icon, reminding us that the mosquito must survive this entire period without dying from natural causes. Finally, on the right, the cycle completes with the second bite, transmitting the disease to a healthy human. Having seen how the transmission cycle works, we must recognize why this matters on a global scale. Because of this highly effective biological cycle, mosquitoes are widely considered the deadliest animals on Earth. They are responsible for killing hundreds of thousands of people every single year. When a disease spreads unchecked, it can completely crash local healthcare systems and severely damage national economies. If we do not deeply understand the mechanics of how these diseases are transmitted, we cannot develop effective vaccines, life-saving treatments, or control strategies to protect vulnerable populations. This immense global threat brings us to a critical question. How do scientists predict if a single sick person will start a massive outbreak? Think of an infected person like a tiny spark in a vast, dry forest. If the wood is dry and the wind is blowing hard, you get a catastrophic forest fire. In our scenario, the wind is the local mosquito population. We desperately need a way to measure exactly how strong that wind is blowing. To do this, we must move away from simply guessing about disease spread and instead use rigorous mathematical tools to predict it. Before we look at the actual math, let us identify the key components that make up this mathematical wind. First, we have to know the ratio of mosquitoes to humans in the area. Second, we must account for the biting rate, keeping in mind that the mosquito must bite twice to transmit the disease. Third, we have to calculate the probability that the mosquito actually survives the pathogen's incubation period. Finally, we must factor in the daily mortality rate, because mosquitoes are constantly dying off naturally. These biological realities form the foundation of our mathematical model. Now that we have identified the biological components, we can combine them into a brilliant mathematical concept called vectorial capacity. This formula calculates the daily rate at which future infections arise from one currently infected person. C represents the vectorial capacity. In the numerator, M is the ratio of mosquitoes to humans. The variable A is the daily biting rate, and it is squared because the mosquito must bite twice. The term P to the power of N is the probability the mosquito survives the incubation period. Finally, we divide by the negative natural logarithm of P, which represents the daily mortality rate of the mosquito population. If the biting rate increases, the capacity shoots up dramatically because it is squared. If survival drops, the capacity plummets. Let us see this formula in action with a concrete example. Imagine a village with 10 mosquitoes per person, a biting rate of 0.5 bites per day, a survival rate of 0.8, and a 12-day incubation period. We want to find the outbreak risk. First, we square the biting rate to get 0.25, representing the double bite requirement. Next, we raise the survival rate to the power of 12, finding that only about 6.87% of mosquitoes survive the incubation. We then find the mortality rate in the denominator. Plugging these into our formula, we get a vectorial capacity of approximately 0.77. Because this is less than 1, the disease will likely die out rather than cause an explosive outbreak. Now that we have calculated the baseline risk, let us see what happens when public health workers distribute insecticide-treated bed nets in the exact same village. The nets physically block mosquitoes, dropping the biting rate to 0.2. The insecticide drops the survival rate to 0.5. We square the new biting rate to get 0.04. We calculate the new survival probability, which plummets to a microscopic 0.024%. The mortality rate in the denominator increases significantly. When we plug these new values into our formula, the vectorial capacity drops to approximately 0.00014. This means one infected person now generates virtually 0 new infections. This dramatic mathematical result we just calculated proves exactly why interventions like bed nets are so powerful. By physically blocking the mosquitoes, we reduce the biting rate, which is the most sensitive variable because it is squared in our formula. Furthermore, the deadly insecticide lowers the daily survival rate, ensuring that the vast majority of the mosquito population dies long before the parasite is ready to be transmitted. This shows us that even a relatively small reduction in biting frequency and survival severely cripples the entire transmission cycle, saving countless lives by breaking the chain of transmission. To wrap up our lecture, let us review the key takeaways. First, we learned that mosquitoes are biological vectors that transport deadly pathogens from person to person. Second, we discovered that we can mathematically predict the risk of an outbreak using the vectorial capacity formula, which accounts for biting rates, survival, and incubation periods. Finally, We saw firsthand how public health interventions like bed nets disrupt this delicate biological timeline, mathematically halting the disease in its tracks. You now have a solid understanding of both the biology and the mathematics behind mosquito-borne diseases.